Welcome back to ByteLearn. In this video, we cover the CAP theorem, one of the most referenced and most misunderstood ideas in distributed systems. CAP is not just a theoretical constraint, it is a design decision that every database, cache, and distributed service makes, usually without telling you. By the end of this video, you will understand exactly what that decision is, why it is unavoidable, and how to make it correctly when designing a system. Scenario: your bank's database cluster loses connectivity between two data centers during a network outage. Requests are still arriving. Two choices. Option 1: serve every request from whichever data center is reachable, but that data center might have a stale balance. A user's last transfer has not propagated. You show the wrong number. Option 2: reject all requests until the network recovers, return an error. Availability is 0 during the outage, but you never show incorrect data. Which failure mode is acceptable? That choice, consistency versus availability during a network partition, is the CAP theorem, and it is not optional. Every distributed system makes it whether or not the engineers thought about it. Every distributed system you work with has already made a CAP choice, often without making it explicit in the documentation. ZooKeeper, which Kafka relies on for leader election, is CP. It returns errors during a partition rather than risk electing two leaders. Cassandra is AP. It accepts writes on all reachable nodes during a partition, then reconciles when the partition heals. Traditional relational databases like PostgreSQL and MySQL are CA, but CA only works if partitions never happen, which means they are only safe inside a single data center. The CAP theorem forces you to acknowledge that partitions will happen and decide what you sacrifice when they do. We start with what a network partition actually is and why pretending partitions will not happen is the most dangerous assumption in distributed systems. We define all three CAP properties precisely. We then trace what CP systems and AP systems actually do during a partition. With animated diagrams, we position 12 real systems on the CAP triangle. We cover PACELC, the extension that handles the equally important latency versus consistency trade-off when there is no partition. And we finish with the interview framework that picks the right CAP choice for any system design question. Two audiences: if you are a backend engineer making technology choices, picking between DynamoDB and PostgreSQL for user data, or between Cassandra and MySQL for time series data. This video makes the trade-off explicit so you can choose consciously rather than by instinct. And if you are preparing for system design interviews at companies like Google, Amazon, Zerodha, or Flipkart, the CAP theorem is a separating question. Candidates who can reason about CP versus AP are the ones who get the offer. This video makes that reasoning automatic. Stay till the end. The CAP theorem only describes what happens during a network partition, but partitions are rare. In steady state operation, the 99.9% of time when there is no partition, you still face a trade-off between latency and consistency. Do you wait for all replicas to acknowledge a write before returning, or do you return immediately and let replicas catch up asynchronously? PACELC is the framework that makes this trade-off explicit. Cassandra and DynamoDB expose it as a configuration parameter. Most engineers using those databases have never heard of PACELC. You will. Two prerequisites. Episodes 5 and 6 covered database, sharding and consistent hashing, specifically how data is distributed across multiple nodes using a hash ring, and how replication factor works. We reference those concepts here. If you have not watched them, watch first. Links are in the description. Everything else in this video we build from first principles. The CAP theorem, proved by Eric Brewer in 2000, states that a distributed system can provide at most two of these three guarantees simultaneously. Consistency: every read sees the latest write. Availability: every request gets a response. Partition tolerance: the system keeps working despite network partitions. The critical insight that most explanations miss: partition tolerance is not optional. Any system running across multiple machines will eventually experience a network partition. A dropped packet a data center outage, a switch failure. You cannot choose to skip P. The real choice is, during a partition, do you sacrifice C or A? This is the most important sentence in this video. Partition tolerance is not a choice. If your system runs on more than one machine, partitions will happen. Networks fail, routers drop packets, data centers lose connectivity. The choice is not P versus no P. The choice is, given that a partition has occurred, what do you do? Serve data that might be stale, sacrificing consistency, or return an error until consistency is restored, sacrificing availability, CP or AP. That is the only real choice. Real distributed systems cluster into two camps. CP systems, ZooKeeper, HBase, HCD, Redis in default mode, return errors during a partition rather than serve potentially inconsistent data. AP systems, Cassandra, DynamoDB, CouchDB accept reads and writes during a partition, knowing that data may be inconsistent across nodes, and reconcile when the partition heals. Traditional relational databases, PostgreSQL, MySQL, appear to be CA, but CA is only achievable when partitions are assumed not to happen. In a real multi-data center deployment, PostgreSQL must choose CP or AP just like everything else. Normal operation. Two data centers connected by a network link. Clients in data center west write to the primary database node. The write replicates across the network link to replicas in data center east. Every replica has an up-to-date copy of the data. Reads from any replica return the latest value. A client writes, set balance to 5,000 rupees. The request crosses the network link to the primary database node in data center east. The primary acknowledges the write. The write replicates from the primary to replica B and from replica B to replica C. All three replicas are consistent. Any read from any replica returns 5,000 rupees. The network link between data centers fails. A switch failure, a cable cut, a BGP routing error. Any of these can cause it from this moment. Data center west and data center east cannot communicate. Messages sent from one side never arrive on the other. This is the partition. Clients do not know the partition has happened. Requests keep arriving. A user in data center west wants to update their balance to 3,000 rupees. The request reaches the network link and stops. The system must decide what to do. This is the cap choice. Two options. Option 1. CP. Reject the write. Return an error to the client. The write will not be applied until the partition heals and both data centers agree. Consistency is preserved. No stale data, but availability is 0 during the partition. Option 2. AP. Accept the write from data center west, applying it locally. Simultaneously, data center east might accept a different write for the same key. When the partition heals, both sides have conflicting values that must be reconciled. Availability is maintained, but consistency is sacrificed during the partition. Consistency in the cap theorem has a specific meaning: linearizability. Every read must return the value of the most recent write, as if all operations happened on a single node in a well-defined order. If a client writes value X and then reads, the read must return X. If a different client reads immediately after the write, that client must also return X, not a previous value. Importantly, if the system cannot guarantee this, because a replica is out of sync during a partition, it must return an error instead of a stale value. Consistency is the guarantee of correctness at the cost of availability. Availability in the cap theorem means every request to a non-failed node receives a response, not an error. The response does not have to contain the most recent write. It may be stale, but it must be a real response, not a timeout or a 53 error. This is why AP systems are described as always on. They serve requests, regardless of what is happening in the rest of the cluster. The trade-off is that the response might not reflect the latest state of the system. Partition tolerance means the system continues to operate, accepting reads and writes, even when network messages between nodes are lost or delayed indefinitely. Note: this does not mean partitions are handled gracefully. It means the system does not simply stop working. A system without partition tolerance would halt the moment any network message was lost. No production distributed system can afford that. Partition tolerance is the baseline requirement, not a feature. Traditional databases claim to be CA, consistent and available, but not partition tolerant. This works when all nodes are in the same physical machine or the same local network, where the probability of a partition is near zero. Once you deploy across multiple data centers or across cloud availability zones, partitions become inevitable. AWS, GCP, and Azure all document multi-AZ network isolation events. Assuming partitions will not happen is the same as assuming your data center will never have a network issue. That assumption will eventually be wrong. The real decision, restated clearly, partition tolerance is mandatory. You cannot opt out of it in a distributed system. The choice you actually make is between CP and AP. CP systems say, during a partition I will return errors rather than serve data I cannot guarantee is current. AP systems say, during a partition I will serve the best data I have, even if it might be stale, and I will reconcile inconsistencies when the partition heals. Neither is universally better. The right choice depends on what kind of incorrectness your system can tolerate. A CP system during a partition, the client is in data center west. The primary database is in data center east. The network link between them has failed. The client sends a bank transfer, debit 1000 rupees for a banking system. This write must be consistent. Showing the wrong balance to any user is a compliance violation and a financial risk. The CP system will not apply this right until it can guarantee consistency. The network link is down. The request cannot reach the primary database in data center east. The CP system detects this either via timeout or via explicit partition detection and must decide, apply the write locally on a potentially stale replica or reject it. The CP system rejects the write. It returns a 503 error to the client. The client cannot complete the transfer. This is inconvenient. The system is unavailable during the partition, but it is safe. No user will see a wrong balance. No transfer will be double applied or lost. When the partition heals and the primary is reachable again, writes resume, ZooKeeper, HBase and etcd all behave exactly this way. Error over inconsistency every time. CP systems in practice. ZooKeeper used by Kafka for leader election cannot afford to elect two leaders simultaneously. Electing two leaders is worse than electing none. HBase uses ZooKeeper for exactly this reason. etcd, the Kubernetes configuration store, is CP. A stale Kubernetes state is more dangerous than a brief unavailability. MongoDB in its default configuration reads from the primary, making it CP. Zerodha's trading engine, where wrong balance means regulatory risk, must be CP. The pattern, any system where inconsistency causes more damage than unavailability should be CP. An AP system during a partition. The network link has failed. Data center west and data center east are isolated. The AP system decides, keep serving requests on both sides independently. Consistency will be reconciled after the partition heals. The partition is active. Messages between the two data centers are dropped. The AP system does not return an error. It keeps all replicas available for reads and writes. A client device in data center west updates a user's last seen location to Mumbai. The write reaches replica A directly, bypassing the broken cross data center link. The AP system applies it immediately. No error, no waiting. The user gets a successful response. Replica A returns 200 OK to the DC West client. The write is durably stored on replica A. The user sees success. Availability is preserved. This is the AP guarantee. The fact that replica B on the other side of the partition does not yet have this update is an accepted trade-off. Meanwhile, the same user opens the app on a different device in Data Center East, still isolated from DC West. That device updates the same user's last seen location to daily replica B, which is also accepting writes independently, applies it. Now, both sides have committed conflicting values for the same key. Replica A says Mumbai, replica B says Delhi. Both writes were accepted. This is the consistency trade-off of AP. Replica B returns 200 OK to the DC East device. Both clients received successful responses. Both replicas are available. But the system is now inconsistent. Two different values for the same key exist across the partition. This divergence is the price of availability. The system now has divergent state. Two replicas disagree on the value of the same key. For a social application tracking last seen location, this is acceptable. The location will self-correct within seconds when the partition heals. No financial damage, no compliance risk. This is exactly the AP trade-off. Accept temporary inconsistency, maintain availability, reconcile after. When the partition heals, the two replicas exchange their diverged writes. The system runs conflict resolution. For simple values, Cassandra uses last write wins. The write with the more recent timestamp wins. For more complex cases, DynamoDB uses vector clocks to detect the conflict and surface it to the application for resolution. In either case, the system eventually reaches consistency, hence the term eventual consistency. For location data, social feeds, and product catalogs, eventual consistency is fine. For bank balances and inventory counts, it is not. AP systems in practice: Cassandra, Instagram, Apple, iCloud, Netflix, AP with configurable consistency levels. DynamoDB, Amazon's own shopping cart in AP mode by default. DNS, the most widely used AP system in existence. When a DNS record changes, different resolvers see different values for minutes or hours. That is eventual consistency at global scale. Swiggy's order feed can show a 1 second still delivery location. Acceptable. WhatsApp's read receipts may arrive slightly out of order during a partition. Acceptable. The pattern: any system where temporary staleness is tolerable and availability is critical should be AP. CP systems prioritize correctness over uptime during partitions. ZooKeeper uses the ZAP consensus protocol. A majority quorum must agree before any write commits. Loose quorum, and ZooKeeper stops accepting writes rather than risk split brain. etcd uses Raft, same guarantee. Redis cluster in its default configuration requires that the primary shard be reachable for writes. MongoDB reads from the primary by default. If the primary is unreachable, reads return an error until a new primary is elected. These systems are used wherever incorrect state is more dangerous than downtime. Leader election, configuration management, distributed logs, trading engines. AP systems prioritize uptime and partition resilience. Cassandra uses a tunable consistency model. You configure the number of replicas that must acknowledge a read or write, one quorum all, at consistency level 1. Cassandra is fully AP at consistency level all. It approaches CP. DynamoDB's default is eventually consistent reads AP. With strongly consistent reads enabled, it moves towards CP at the cost of higher read latency. DNS is AP by design. Authoritative servers update records and let the change propagate to resolvers over minutes to hours. Availability of DNS is more important than immediate global consistency. Traditional relational databases, PostgreSQL, MySQL, Oracle, are described as CA. This is correct in a single data center deployment where network partitions between replicas are extremely rare and brief. The moment you deploy PostgreSQL across multiple availability zones or data centers, you face the same CP or AP choice as everyone else. PostgreSQL streaming replication with synchronous commit on is CP, writes block until the replica confirms. With synchronous commit off, it becomes AP, writes return immediately. Replica may lag. The configuration parameter is the cap choice. MongoDB sits in an interesting position. By default, reads go to the primary CP, but MongoDB allows read preference settings: primary preferred, secondary nearest. Reading from a secondary gives you potentially stale data, AP behavior. Write concern W1 is AP. Write concern W majority is CP. The write must be acknowledged by a majority of replica set members before returning. MongoDB's cap position is a dial, not a fixed point. This is increasingly common. Cassandra, DynamoDB, and MongoDB all expose their cap position as configuration. Indian production systems make explicit cap choices. NPCI's UPI infrastructure is CP. A payment acknowledgement must be consistent. Showing the wrong transaction state to a merchant is a settlement risk. Zerodha's trading platform is CP. Wrong portfolio balance shown during a partition is a regulatory violation. Swiggy's order feed and delivery tracking are AP. 1 second stale delivery location is invisible to users. Aadhaar's red heavy identity lookup is AP. Slight staleness in a non-critical read is acceptable. The cap choice maps directly to the business risk of each system. Cap only describes the partition scenario. PACELC, proposed by Daniel Abadi, extends it to steady state. The else branch, when there is no partition, distributed systems still face a trade-off between latency and consistency. If a write waits for all replicas to acknowledge before returning, strong consistency, high latency. If a write returns after one replica acknowledges and replicates asynchronously, low latency, possible stale reads. Cassandra's consistency levels are a direct PACELC dial. Consistency level 1 returns after one replica acknowledges, lowest latency, highest risk of stale reads. Consistency level quorum requires a majority of replicas to acknowledge balanced. Consistency level all requires every replica, highest consistency, highest latency. For most Cassandra deployments, quorum is the right balance. It tolerates one replica failure while keeping latency reasonable. DynamoDB exposes PACELC as a per request parameter. Eventually consistent reads. The default are served from any available replica. They may be up to 1 second stale, but they are fast and cheap. Strongly consistent reads always go to the leader node. They are never stale, but they cost twice the read capacity units. For most DynamoDB use cases, eventually consistent reads are correct. For cases where you need to read your own writes immediately, use strongly consistent reads and pay the extra cost. The practical insight cap tells you how to handle the failure case, the 0.1% of time when a partition occurs. PACELC tells you how to optimize the 99.9% of time when there is no partition. For most user-facing applications, the majority of reads can tolerate 1 second staleness. You should choose EL and get low latency. For writes that affect financial state or distributed coordination, you need EC. Design your system to use EL for reads and EC for critical writes. This is exactly what DynamoDB's write consistency flags let you do. First question, which failure mode causes more damage to your system? For a bank, showing a wrong balance is worse than showing an error. For a social feed, showing a post from 2 seconds ago is better than showing nothing. For a trading platform, an incorrect portfolio value is a regulatory violation. For a delivery app, a 1 second stale location is invisible to users. Answer this question first. The answer directly determines CP versus AP. Second question, what category is this system? Financial transactions, inventory management, distributed coordination, and compliance systems should be CP. The cost of inconsistency, wrong balance, oversold inventory, two leaders elected exceeds the cost of temporary unavailability. Social feeds, product catalogs, user presence, delivery tracking, and analytics should be AP. Temporary staleness is invisible to users, and availability is the primary reliability metric. Third question, what happens if two replicas accept conflicting writes during a partition? For last seen location, last write wins works. For a shopping cart, union of both carts is acceptable. For a bank balance, there is no safe merge of two conflicting balance updates. You must prevent the conflict, which means CP. If your data type supports conflict-free merging, last write wins. Union, max, you can safely be AP. If merging conflicting values produces an undefined or dangerous result, you must be CP. Fourth question, does your chosen database let you configure the trade-off? Modern distributed databases have moved away from fixed cap positions. Cassandra, DynamoDB, and MongoDB all let you set consistency level per operation. This means you can be AP for reads, low latency, eventual consistency, and CP for critical writes, quorum acknowledgement. Design your application to use the right consistency level for each operation type. Rather than choosing one setting for all operations, this is the sophisticated answer in a system design interview. The interview answer that distinguishes you. Start with the failure analysis. What breaks if the system shows stale data versus what breaks if it shows an error? Pick CP or AP based on that analysis and justify it. Name a database that implements your choice, ZooKeeper or HCD for CP coordination, Cassandra or DynamoDB for AP with eventual consistency. Then mention that modern databases let you configure the trade-off per operation. Quorum writes for critical paths, eventual reads for high throughput paths, 4 components, one complete answer. That shows you understand CAP as a design decision, not just a theorem. Before the CAP theorem was formalized, distributed databases tried to be CA consistent and available, with partition tolerance treated as a bonus rather than a requirement. When partitions occurred, and they always did, those systems had no defined behavior. Some returned corrupted data, some split brained, some simply stopped working. The CAP theorem forced the industry to acknowledge that partition tolerance is mandatory, that the CA claim is false in distributed environments, and that every system must explicitly choose its failure mode. That shift from pretending partitions do not happen to designing for them explicitly changed the architecture of every distributed system built after 2000. Eric Brewer stated the CAP conjecture at ASOS P2000. Gilbert and Lynch formally proved it in 2002. Amazon's Dynamo paper in 2007 was the first production system to explicitly embrace the AP side of CAP, accepting that consistency could be sacrificed during partitions and designing a complete reconciliation mechanism to restore it. That paper directly inspired Cassandra, React, CouchDB, and DynamoDB. Every distributed NoSQL database you work with today is a variant of the design choices made in that 2007 paper. Understanding CAP is understanding the intellectual foundation of the modern distributed data stack. India's largest distributed systems make explicit CAP trade-offs at national scale. UPI, handling 90 lakh crore rupees in annual transactions, is CP. The NPCI cannot afford to show wrong payment status. Aadhaar makes a split choice. CP for identity rights, enrollment must be consistent. AP for authentication rates, 1.4 billion queries per day, demand availability. Flipkart's Big Billion Days uses AP for the product catalog. A 1-second stale price is acceptable, but CP for inventory counts, overselling a product, is a financial and reputational risk. Razorpay is CP, a payment gateway that accepts during a partition and shows wrong status is unusable. Each of these is an explicit CAP decision made by engineering teams who understand exactly what they are trading away. The CAP theorem is the reminder that distributed systems cannot be everything to everyone. Partitions will happen. You will have to choose. Choose consistency, CP, and your system is always correct but sometimes unavailable. Choose availability, AP, and your system is always on but sometimes stale. Neither is universally correct. The right answer depends on what kind of incorrectness your business can tolerate. Now you know how to make that choice, justify it, and implement it. And you know the PACELC extension that governs the trade-off even when there is no partition. Design consciously. That is the CAP theorem from the network partition scenario. Through the precise definitions of consistency, availability, and partition tolerance, through CP and AP systems in action, through real system positioning, through PACELC for steady-state design, and through the interview framework, you now understand CAP not as a piece of trivia, but as a design decision that every distributed system makes, and that you can now make correctly. Here is what you can now do. Explain precisely why partition tolerance is mandatory and why the real CAP choice is CP versus AP, not CA versus everything else. Position any distributed system on the CAP triangle and explain why it sits there. Apply PACELC to reason about the latency versus consistency trade-off in steady state. and give a complete interview answer. Start with failure analysis, pick CP or AP, name a database, mention per operation consistency configuration. Next video, how load balancers work. You now understand how data is distributed across shards and how consistency is managed across replicas. The next piece of the architecture is the load balancer, the component that distributes requests across multiple servers. Episode 8 covers the two types of load balancing, layer 4 and layer 7, the algorithms load balancers use to pick servers, and how consistent hashing at the load balancer connects back to everything you learned in episodes 5 and 6. Link in the description. Subscribe to ByteLearn for one system design concept per week, explained through animated diagrams, grounded in production systems, and interview ready. Hit the bell. Load balancers drops next Wednesday. One question before you go. Which system surprised you most with its cap position that DNS, the Internet's address book, is AP and serves stale records for minutes, that etcd and ZooKeeper are CP and will stop accepting writes rather than risk a wrong leader, that MongoDB's cap position is a configuration dial you set per query, that UPI is CP and will return an error rather than show a wrong payment status, or that Cassandra lets you choose your cap position on every single read and write. Drop it in the comments. That tells me which examples land best for the follow-up.